This is a cathode ray oscilloscope image of two sound waves. Because the oscilloscope can display what might otherwise be invisible, it has become a common tool of science and technology. There are many kinds of oscilloscopes that vary in function and appearance, but the principles at work in them are much the same. These principles are the subject of our film. The discovery of the cathode ray tube, heart of the oscilloscope, goes back to early experiments in electricity. Scientists observed a high voltage discharge through air. They wondered what it would look like in a glass tube with most of the air removed. They attributed this effect to something from the cathode, which they named cathode rays. Once cathode rays were discovered, investigators shaped new tubes to study them. This one was designed to test if cathode rays, now known as electrons, travel in straight lines. The light on this cross travels in straight lines. Therefore, the shadow is shaped like the cross. It was learned that in this respect, cathode rays and light are similar. Both travel in straight lines. It was found that electrons act like particles capable of giving momentum to this pinwheel. It was also discovered that these particles are charged and can be deflected by magnetic or electric fields. Early discoveries such as these laid the foundation for the design of cathode ray tubes now used in television, sonar, radar, and the cathode ray oscilloscope. This simplified animation demonstrates how the cathode ray tube works in an oscilloscope. When electrons leave the hot cathode in the electron gun, they travel in a straight line toward the fluorescent screen. As electrons move down the tube, they pass two metal plates. Undeflected, the beam produces a spot like this. But it is only by moving the spot that it becomes useful to us. We have learned that the electrons can be deflected by an electric field. Therefore, by charging the plates, plus and minus, the beam is deflected. The voltage applied to these plates determines the direction and amount of deflection. The terminals on this battery are arranged so that various voltages are available. The relationship of voltage to deflection is so precise that a cathode ray oscilloscope can be used as a voltmeter. The second set of plates in a cathode ray tube controls the horizontal deflection. By changing the voltage on these plates, the beam is deflected horizontally. A special circuit has been connected to this voltmeter, providing a repetitive sweep voltage. By connecting this voltage source to the horizontal plates, we achieve a regular horizontal sweep. This kind of circuit is built into the oscilloscope, and its speed can be controlled by the sweep rate knob. This circuit is like a precise built-in clock, capable of rapid sweeps. A slow sweep rate can be timed by a stopwatch. On the front of the oscilloscope screen is a set of graph lines the vertical or y-axis represents voltage. The horizontal or x-axis can represent time. In this demonstration, a battery's voltage is plotted against a slow time base. These twisted wires produce a small amount of voltage when heated. Since the oscilloscope responds only to voltage, this simple thermocouple is a transducer, allowing us to plot temperature against time on the oscilloscope. To convert sound into voltage, we use a microphone as a transducer.
The rain in Spain stays mainly on the plain. The rain
If
in
the signal
Spain
is too
stays
weak,
mainly
the
on
oscilloscope
plain.
can amplify it.
The rain in Spain stays mainly on the plain. The rain in Spain stays mainly on the plain.
With the oscilloscope, we can analyze sound waves. This pure tone gives us the classic sine wave. Increasing the frequency causes the waves to bunch up. Musical sounds are made up of combinations of these pure tones. A photocell is a transducer that converts light into voltage. Here's a problem. How long did the flash stay on? By knowing the speed of the horizontal sweep, our built-in clock, we can graph the intensity of the flash bulb. This special oscilloscope is triggered by the flash signal and can store the image. With an oscilloscope and a microphone, we can graph investigations in sound. With an oscilloscope and a photocell, we can time the shutter speed of a movie projector. By applying sine waves to both the horizontal and vertical inputs, we can graph the relationship of two waves. These patterns are called Lissajous figures. Beyond its scientific and technical uses, even the artist can discover new forms of graphics with a cathode ray oscilloscope.